And we're back. Hey folks, this is DJ HeroBot here with his, well, counter thing. Here to give you a full tour of exactly how it works. So, the very first thing that is needed by any sort of counter or clock is, well, a clock. Now, the way clocks work in Minecraft is you have a bunch of repeaters, which are these guys here, and a bunch of NOT gates, which are these guys here, all strung together in a nice long chain. Now the way that works is when one of the outputs changes, it is chained to the next one. However, since each torch takes exactly one tick to respond to its input, if you have a long enough chain, you end up with this sort of cyclic delay line, I like to say. Now, the reason why I call it a delay line is that it's pretty much exactly like Mercury delay line memory worked back in the, late 1940s, early 1950s, before they discovered core memory for their mainframes. Anyway, the main reason why the clock is so slow with this thing, as you can see, is that, admittedly, I didn't try to do any sort of synchronization with all of the other circuitry, so as I pass the bits up to higher floors, as I have to stick more and more repeaters or NOT gates in there, it induces delays into the signal. So I have to clock it slow enough to give all of the bits time to settle before it moves on to the next number. Otherwise I would just display gibberish on the display, which we don't want. Now, the very first thing after the clock, of course, is going to be the counter itself. Now, the counter is based off of the 74LS390, which doesn't mean anything to most of you, but for anybody who has an electrical engineering background, you'll know that it's a decade counter integrated circuit. Well, this is only half of one, actually, just because I only have one digit that I'm currently counting. And what a decade counter is, as the name implies, it counts from 0 to 9. That floor down there is bit 1, this floor is bit 2, that next floor is bit 3, and the floor above it is bit 4, because you need 4 bits to represent a number in the range of 0 to 9. Now, if I was smart, I would have actually made it into a hex counter. The reason why I say that is because, well, you have to have a whole bunch of glue logic in order to roll over on a non-power of 2 number, which 10 is not a power of 2, so I have to have this AND gate here, and a whole bunch more logic over yonder on that floor, and so on, in order to make it roll over to 0 after a 9. Anyway, this part isn't very interesting, so let's move on to the next bit. As we walk, I'll talk. One major problem that I ran into is the fact that I should have used toggle flip-flops. I ended up using JK flip-flops instead. The reason why is because I used the I used the National Semiconductor datasheet, which specifies JK flip-flops in its logic diagram. Then I switched to the Fairchild diagram later on after I realized the National Semiconductor one was, well, as they say, bullshit. The Fairchild one just used simple toggle flip-flops, but at that point I had already had the stack of all 4 bits built, and, well, fuck it. At any rate, what we have here on these 4 floors, 0, 1, 2, and 3, we have the 4 bits of a full adder. Now, what a full adder does is it adds bits with a full carry in and carry out. Now, the carry in normally comes in right here, and it ends up carrying out right here, gets fed up, bust along here, and fed up to the exact same point on the next floor where the carry-in is. But that doesn't matter. What we have here are the 2 most important things, operand A and operand B. For now, operand A is currently tied to 0 because we just want to pass along the output from the counter over there. So we have E bit 0 right here, and if we go up to the next floor, we have E bit 1, and so on and so forth. The really complex bit from this point over to the right is the 74LS47 BCD-to-7-Segment Decoder. Now, what that horrible mishmash of text speak means is it takes a binary coded decimal number, that is a number in the range of 0 to 9, and it converts it to a 7-segment display. Now, you don't actually know what a 7-segment display is, probably, but if you think, you actually encounter them pretty much every day of your life. You look at a digital clock on your car, that's a 7-segment display. It has 7 LEDs that combine to form a number. Microwaves have variations of that, display letters sometimes. Your alarm clock probably has a 7-segment decoder, all sorts of things. At any rate, each one of these floors is dedicated to one of these 7 segments. At the very bottom here we have segment A, segment B, segment C, and so on up through segment G. Now, each segment is just a bunch of AND gates and NOT gates that ultimately determine whether or not the segment is lit or not. The reason why it has to do all this is because there's no real easy way to go from a binary number, which is in 4 bits, to some arbitrary combination of 7 bits, 1 bit for the 7 segments. So I pretty much had to plug all of this in based off the datasheet. So what we have over here is we have the line drivers. We have bit 3, 2, 1, and 0, as we see tick over from 1 to 2. Now we have D, not D, C, not C, B, not B, A, and not B. And the reason for pre-knotting everything is because, well, honestly, all of the segments need some combination of the other, or need some combination or the other, so it's better to just have some sort of standard circuitry that I can duplicate across each floor. Now, right here, 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 and here, we see the bus points where we carry the A, B, C, and D signals up to each subsequent floor, which unfortunately induces some lag in the actual digit, which we compensate for later. So, let's take a look at segment A's repeater shaft in order to bus it up to the surface. Now, the main important thing, and the main real pain in the ass thing with circuitry in Minecraft, is that redstone dust only lasts 15 blocks before you have to repeat it. So, every so often I have to have this sort of repeater well thing where I have a NOT gate here and a NOT gate here in order to not actually affect the signal. And that regenerates it far enough to go another 15 blocks, at which point I have to repeat it yet again, and yet again, and in a moment, yet again, and so forth until we get to the surface. Honestly, this is pretty much the most time-consuming bit of constructing all of this. Hey, we can see all of the other repeater shafts passing all of the signals up to the surface here. So here we have the output of segment G. And do I have my sign up here? No, I don't have my sign anymore. Damn. Anyway, over here we have E segment C, E segment G, and all of E other segments. Now, the really clever bit is, let me get over here real quick. The real clever bit is this stack of 7 latches. Now, if you think of a door latch, what it does is it relies on human intervention to change position, but once it changes position, it stays there. In this case, there is no human intervention, but there is the intervention of this clock here. And what a clock does, as we discussed, it generates a pulse, and this pulse is transmitted over here to the clock input of each latch. The actual data input to each latch is each segment. So what we end up with, oh balls. What we end up with are 7 outputs that all change exactly simultaneously, thanks to the clocking of the latch. The reason why this is necessary is because, as I mentioned way back at the start of the video, it takes different amounts of time for the signal to go to, say, segment B, as it does to go to segment F, because there's a different number of repeaters and a different number of NOT gates and other bits and bobs that take time to process. Thanks, Notch. At any rate, we have these extremely long wires taking the signal over to this wall here from the latches. And if we're lucky, and I haven't broken anything on the way, we see our 7-segment display. It's currently showing a 7. Now it's showing an 8. And if I blather on meaninglessly for a little bit longer, as I have been for this entire video, we see it turns to a 9. And come on, baby, show us a 0. There we are. And that's about the size of it. All of that is necessary to count from 0 to 9 infinitely without any kind of intervention. Kind of sad when you think about it. Well, this is DJ HeroBot signing off, and hopefully the next time I talk to you guys, this will all be filled in with glorious, glorious circuitry. Ta-da!